All right, so the last one we looked at graphing exponentials. Now we're going to look at solving equations with exponents. And we've looked at these before, I know, because I've looked at them with freshmen already this year. So I know that you've seen something that looks like this. And looking at it, I've got 3 to the 2x is equal to 9. And the problem that we've got is x is up there in that exponent. So I can't just get rid of the x. Instead, what I've got to try to figure out a way to do is to rewrite my equation so that I can come up with something that's helpful. If I'm going to look at this 9, I know that 9 is equal to 3 squared. If I can rewrite these as exponents with the same base, then I know that my two exponents are going to have to be the same, regardless of what they are. So if I've got 3 to the 2x is equal to 3 squared, then I know I can write another equation. Not with a 3 though, right? I can do what was called looking inside. That's what we called it in Math 1. We can look inside the equation to find two quantities that we know have to be the same. If my bases are the same, then I know I've got to have my exponents be the same. And so then in this case, it gives me a nice simple equation to solve. Let's look at another one. Let's look at one that maybe doesn't look quite so simple. Let's say I've got 16 is equal to 2 to the 3x minus 18. Here, I'm going to look at my 16. I can rewrite 16 as 2 to the 4th. This one has a base of 2, so I know that I can use it. I've got 2 to the 4th is equal to 2 to the 3x minus 18. That means that because I have the same base, I know that my exponents have to be the same. So 4 is equal to 3x minus 18. I can solve from here. I can add 18 to both sides, divide both sides by 3, and I get that x is equal to 22/3. Sometimes you might have to deal with things that have negative exponents. Something like this. Let's say I've got 2 to the x squared plus 2x is equal to 1/2. Now it looks like I'm going to have a really hard time writing these as the same base, but if I look at this, I have to remember that 1/2 is equal to 2 to a negative 1 power. So as soon as I do that, I've got 2 to the x squared plus 2x is equal to 2 to the negative 1. So simple as that. I now have it in a form where I can see my new equation show up. I can add 1 to both sides so that I've got everything on both sides, or on one side here. And then I can factor and solve. This is a perfect square trinomial. So I get that x is equal to a negative 1. Oops, you can't see that there. Sorry. There we go. So x is equal to a negative 1. Now, they're not all going to be that nice and simple. Sometimes they might look a little bit more complicated. We also are going to be looking at some where we have e show up. And e is something, it's a number that's very similar to pi. If we remember, pi is an irrational number. Oops, that's a 10. Pi is an irrational number. E is also an irrational number. I have got a great video that I linked on my plan book. It's not mine. It's much better than any of the stuff that I'm coming up with. But it gives a good example as to where it comes from and lets you know how it showed up. It shows up in compound interest and in things like continuous population growth. So we're going to look at it when we look at some applications here too in a minute. At this point, all that it is it's just a base. The problem that we've got is on this side, I've got 2 of them. And I can't rewrite it unless I have a base exponent equals a base exponent. That's the form that we want to get that into. So on this side, everything's going to stay the same, but over here, I have to remember my exponent rules. I'm multiplying with the same base, so that means I must add my exponents together. Now, I've got my exponents, so now I can rewrite it as 3x plus 4 is equal to 10. I can subtract 4, and then x is going to be equal to 2. You might also see it where we've got e to the x squared divided by e squared is equal to e to the x. Yuck. If you looked at that and just said yuck because it's got a fraction, kind of shake your head a little. Remember, fractions aren't bad. In this case, I have division, and I've got the same base. If I'm dividing with the same base, dividing, that means that I have to subtract my exponents. So I can rewrite this as e to the x squared minus 2 equals e to the x. I can look inside. I've got my exponents because I've got the same base. I know my exponents have to be equal to each other. X squared minus 2 equals x. So x squared minus x minus 2 equals 0. From here, I can go ahead and factor. Sorry about that glare from my curtains there. The sun is shining on it. So I've got a minus 2 and a plus 1. So then x is equal to 2. And x is equal to a negative 1. Okay. Now, the last thing that we want to look at for this section is we want to look at some applications of exponential functions. And these are mainly showing up with compound interest and compound growth. Applications of exponentials. And I know you guys are all really, really excited because you know that word application means word problems, right? So the first one that we're going to look at is looking at compound interest. And with compound interest, we have two different formulas. The first one looks like this. I've got A is equal to P times 1 plus R divided by N over, or to all raised to the NT power. And then the other one is going to be A is equal to P e to the RT. So those are the two formulas that you are going to need. And as we're looking at them, we want to pay attention. P shows up in both of them. P is the principal or the initial amount. Right? Maybe you started off with $300 in the bank, or you started off with 100 bacteria in a dish. Right? R is the growth rate. And then that's, T is also in years. Usually, sometimes with this one, if we're dealing with things like bacterial growth, then it doesn't always happen in years. Sometimes it happens in months or hours or something like that, but we'll look and see what that looks like. And then N is the one that shows up here. N is the number of times compounded per year. I'm going to zoom out a little bit. So number of times compounded per year. So for example, if it's compounded quarterly, that means that N is 4, right? If it's monthly, then that means that N is 12 and so on, right? Biannually would mean twice a year, so N is 2. This one right here happens when we're dealing with compounding continuously. And that happens with things like bacteria growth and population growth and things like that. So we're going to look at an example out of the book. We're going to look at, I think it's problem 115. But we've got Edgar, and Edgar made some bad choices. Edgar has $5,000 in credit card debt. And he has a 20% interest rate. So not only has he racked up this debt, but he's going to make another bad choice, and he's not going to pay on it for 2 years. He's not going to pay any minimum payments or anything like that. So we're assuming, obviously, that there's no late fees or, it's not going to collections, but instead it's just going to grow because that interest is going to be compounded. They have a couple of ways that they want us to look at it. The first one is they say, what if it's compounded quarterly? Okay, and so we're going to look at that formula and see if we can identify all of the pieces. So A is equal to P times 1 plus R over N to the NT. Right, so I know that P, that's that initial amount that we started with, so P is going to be 5,000. R is that 20% interest rate. Right, so if I've got a 20% interest rate, remember I always put my percentages in terms of decimals, so 0.20 or 0.2. Okay. T is going to be 2 years. And in this case, because it's quarterly, I know that N is 4. Can you stop, please? Thank you. Sorry. So I'm going to plug my stuff in. I've got A is equal to 5,000, 1 plus, my R is going to be 0.2 divided by 4 for my N, and then 4 times 2. So this is definitely something that you don't want to do by hand. Not at all, because this is yucky. So I'm going to grab my calculator. I'm going to show you how I will plug this in. I'm going to do it all at once. If you want to, you can do it piece by piece, but as long as you're paying attention to parentheses and stuff, then you should be pretty good. I've got 5,000 times, and then in parentheses, 1 plus 0.2 divided by 4, end my parentheses, raised to, remember that's that little caret button, it's right there, raised to, and then in parentheses, I've got to have 4 times 2, or you could just say raised to the 8th power. But if you are going to do them separately, or let's say you've got some yucky numbers here, then you want to make sure to keep those parentheses too, to keep that exponent together. So after 2 years, he will owe $7,387 and then 28 cents. That's a lot of money. For part B, they say, well, what if it's compounded monthly, which is how most credit cards are compounded. So if I've got monthly compounding, then I still have 5,000, right? I still have 1 plus, my rate is still 20%. The thing that's going to change is it's no longer compounded quarterly, instead it's compounded monthly. So N is going to be 12, then I've got 12 times 2. So once again, I can just plug that in. So I've got 5,000 times, oops, let me get that so you can see it without the glare there. That's better. Times, in parentheses, 1 plus 0.2 divided by 12 this time. And that's raised to, in parentheses, 12 times 2. And so in this case, we've got 7,400, not 300 anymore, instead $434.57. So that makes a difference. Compounding quarterly, it grew about $2,387, and then compounded monthly, it grew about $2,400. So that does make a difference. The last one is, what if it's compounded continuously? And you won't find credit cards that do this in the real world, but we're still going to look at our formula. And so I know that my formula is P-E to the RT, or PERT. So I've got 5,000 is still going to be my P. I've got E, and then I've got 0.2, and then I've got 2. So this one's pretty easy to do. All I have to do is my, oops, let me get that there, 5,000 times, I have to figure out where my e to the x is. For me, on my calculator, it's right here, but remember, every calculator is different. So it's times e raised to the, and then I just have to plug in 0.2 times 2, and then end my parentheses. And in this case, with continuous compounding, I've got $7,459.12. So even more than if it was compounded monthly. Not as big of a jump from quarterly to monthly as it is from monthly to continuously, but it still is more. Now the last one that I want to look at, where did my paper go? Uh-oh. The last one that I wanted to look at was in a situation where we're dealing with bacterial growth. So let me actually, it was right here, and I'm sure you're loving me fumble around in this video. There it is. Ah, found it. The last one is looking at a problem like 1/19. And so this is a problem from your paper. So a researcher at the Center for Disease Control and Prevention is studying the growth of a bacteria. He's starting with 100 bacteria, and it grows at a rate of 6% per hour. So my rate is going to be 0.6 per hour. So remember when I said that T is time in years? Except for when we're dealing with this continual growth, it might be hours depending on what your rate is. It's always dependent upon your rate. So if this is per hour, then that means that T is in hours. So they want to know how many bacteria will be there after 8 hours. That's the question that we're dealing with. So I know I've got A is equal to P to the ERT. It's almost like I'm saying party. So I know that A is 100 times E to the 0.06 times 8. Oh, you can't see that because of that glare. I'll try and get my videos done in the morning from now on because this afternoon glare there is really annoying. So I've got, let me put this here so you can, there we go. Let me move that all up. That's good. So I've got 100 times E to the 0.06 times 8, and my parentheses, I've got 161 bacteria. After 8 hours, his bacteria is almost doubled, which is kind of cool. So that should be good to get you through what we're looking at for section 10.2. Remember, if you need any help, email me, comment. If you need to, we can video chat, whatever we need to do to make sure that you are understanding things. Have a great day.